So I think we're all back together now. I was talking a little bit with the two groups who finished early, and we talked about how they were thinking of using color to classify stars and or kind of the shape of the spectra. So looking at this overall shape, seeing ones that had slopes, maybe more negative slopes versus positive slopes, and how that might also relate to color. So from talking with a few people, did anyone think they found any A stars? What stars, what number? You can either shout it out or put it in the chat. A stars with the big hydrogen H alpha lines. Yeah, so maybe star 5 was an A star. Let me see, yeah. Or you can see our H alpha line right there. You can see my cursor. Is a bit steeper, is a bit deeper. Yeah, so I was thinking 5 might be a good one too. Any others? Six. Yeah, definitely 6 has a really deep H alpha line. Another thing, A stars tend to be white. We'll talk about that. This one definitely looks like a good A star. How about O and B stars, those really blue ones? And 10 maybe has an A star? Yeah, look at that H alpha. Very good. As far as blue stars, O and B stars, any O and B stars here? Oh, sorry. Maybe 4? Yeah, definitely. So 4 is very blue. And one thing we can notice, and I was talking a little bit again with the groups who are here, but if you look, you can look at color both looking at these images, but you can also think about looking at the spectra. So you can look at where the spectra peaks, and that'll tell you a bit about the color, because shorter wavelengths are going to be bluer. So 4,000 is going to be pretty blue, whereas 9,000 is going to be pretty red. So since this star is most of its light is coming from near this 4,000 area, it's going to be a really blue star. So we can see that in the image, but even if you didn't have the image, just looking at the spectra, you'd notice that this was probably a pretty dang blue star. So maybe an O or B star. Great. So to look at how astronomers classify stars, one of the main things they use is something called an HR diagram, which is similar to what a lot of you guys had proposed. It uses color as well as the brightness of a star, which I didn't give you, so you couldn't work with, but if I had, so the color and the brightness in order to classify stars. And when we do this, we see some interesting patterns start to emerge. So this is a field of stars, and we can see that these stars have different colors, and we're going to sort them based on color as well as based on their brightness. So right now we're just kind of zooming in on these stars, and we're going to move all of the blue stars over to the left and all of the red stars over to the right, and just kind of sort between, so kind of yellowish stars towards the red, white stars in the middle. So we've now organized the stars based on color. And now they're also sorting them based on brightness, with brighter stars at the top, dimmer stars at the bottom. And we start to see some neat patterns coming out. And so when we sort by color as well as brightness, we see this kind of shape that we call the main sequence. Sorry about that, as well as some other patterns that tell us about what's happening within stars. So a lot of the ways that astronomers classify stars might be based on, like when you looked at the A stars, that depth of the H alpha emission, but it's also often based on color and brightness of the stars. So with the HR diagram, once we have them arranged by color and brightness, we see that some patterns emerge, and we can also start working with the spectral class of these stars. So that's what's shown down here on the x-axis, these letters, O, B, A, F, G, K, M. So a way to kind of remember that order that I like to use is only brave astronomers fight giant killer monsters. So O, B, A, F, G, K, M. O stars and B stars are going to be those blue stars, whereas K and M stars are going to be more red stars. The reason why it's this weird order is because astronomers first were working with the depth of spectral lines. Specifically, they looked at the depth of the H alpha line. So A stars had the deepest H alpha line, then B stars, and kind of working through the alphabet. But back in the early 1900s, Annie Jump Cannon, one of the Harvard computers, noticed that if she reorganized the stars using this method, the OBA-FGKM, the stars would fall really nicely into a few different areas of this HR diagram. So this Hertzsprung-Russell were the men who it gets named after, but Annie Jump Cannon did a lot on organizing the stars based on this new spectral class method to notice that when she did that, the stars with similar properties fell in similar areas on this diagram. So some of you have done for your citizen science project, you've looked at the Star Notes project where you got to look at some of the data that these Harvard computers transcribed, and Annie Jump Cannon is one of those Harvard computers. So working with the data that these women, these early female astronomers who are really fundamental to shaping how we view stars, Annie Jump Cannon is one of those. Little bit of an offshoot. So when we do plot stars using color or temperature versus luminosity, we see some kind of major areas getting filled with stars and some places that are empty. So there's these white dwarfs, which we'll talk about down here. They're going to be very faint, fairly faint, but kind of blue and white. We see a lot of stars falling along something we call the main sequence. The main sequence is where stars spend most of their lives. So most of the time a star is alive, it's going to be on the main sequence. And then as a star dies, it'll turn into a supergiant or a giant before it either explodes or collapses. And we'll get to talk about that next week. We'll talk about stellar death as we wrap up this section. Today, we're going to focus more on star life and what these different classifications will mean. So this is kind of a useful chart that I think I grabbed from your book, but I will try to provide in our tests because it's going to be useful. That shows the mass. When we do use these spectral classes, we notice that all the stars in class O are about 25 times as massive as the sun. They have similar temperatures of around 35,000 Kelvin. They have similar luminosity, so 80,000 times as luminous as the sun. That's what this O dot means, sun. So this is solar luminosities. This is M solar is solar masses. And then we can also, based on the type of star, we can figure out how long it will live, which is really cool. So I don't need you to copy this down. I will always give it to you, but just to show you different spectral classes of stars will have similar masses, similar temperatures, similar luminosities, and will all live for the same time. So all O stars will live about 3 million years, whereas all K stars will live about 15 billion years. And we'll talk about why that is later today. Any questions so far? So now I'm going to tell you just a little bit about all these different classes of stars before we start talking about stellar life cycles. So the first class are O and B stars. So these are our brightest and most massive stars. They don't really have very deep hydrogen lines, and that's because they are so hot, they're so bright, that most of the hydrogen is ionized. So all of the hydrogen has been stripped of its electron. And it's one electron, sorry. So you can't have electrons moving between energy shells if there's no electron there. So we don't really see hydrogen lines in these O and B stars. Because they are so large, their gravitational pressure creates very dense, hot environments that makes fusion happen really, really fast and makes them super, super luminous. So they're really, really massive, which also makes them really, really luminous. So they're very, very bright, very, very big, but there are not very many of them. So when we form stars, it's hard to get stars this big, so we'll only get a few O and B stars whenever we form new stars. The next class of stars is A stars. So these are the stars that have the deepest hydrogen lines. And that's because they're kind of the perfect temperature for getting that electron transition between the third and the second level that produces the H alpha line. So that's what we saw when we looked at the hydrogen emission spectra. The H alpha line was when we went from that third shell to the second shell. And you need the right energy conditions to produce that. And A stars have that perfect right energy conditions for absorbing H alpha lines. So it's not so hot that hydrogen is ionized, but it's also hot enough that there are energetic photons that can be absorbed by this line specifically. A stars are kind of white, so not so they look sort of white. So O and B stars were blue, A stars are more white. They're also the most common star that is visible to the naked eye. So they're not the most common star in number, but a lot of the other stars the more common stars are so faint that we can't see them. So if you go out at night and you look at the stars, most of the stars you're going to be seeing are going to be A stars. That's because the smaller stars, the K and M dwarfs, are really, really faint. So even though there's a ton of them around us, we can't actually see them. The next classes of stars are F and G stars. So these are kind of our medium type stars, stars that are the same mass about as the sun. The sun is a G star. They're cooler and smaller. So instead of being blue or white, they're more peaking in yellow and green, which means that peak wavelength is lower energy. So they're also lower temperature. Kind of a little fun fact, our sun peaks in green light. So even though it might look kind of yellow, it's actually peaking in the green. And that's part of the reason why grass and trees are green. It's so they can absorb sunlight the best possible way they can. And there's some planets we've discovered around red stars where we think if there was grass on those stars, the grass would be red because that would be the ideal color to absorb red light. So just a little fun tangent, but why grass is green on Earth is because the sunlight is actually green. So I think that's cool. We can identify F and G stars both by their green color and also by the really strong calcium lines that we see in G stars, F and G stars. So if we look back at these stars, this might be a F or G star. We can see some deep calcium lines up here in the redder part of the spectrum. This is maybe a G star. These calcium lines we can see are deeper. So that's how we would go about identifying F and G stars. This is probably not an F or G star because it barely has any of these calcium lines. Oops, sorry. Okay. So, and the reason we don't have the strong hydrogen lines is because it's not quite hot enough on these stars to really produce the emission that's necessary to get that hydrogen emission absorption line. So they're cooler than the A stars. Hydrogen isn't ionized, it is there. They're still mostly hydrogen. Any star is going to be about 90% hydrogen, but it's just not hot enough for the H alpha line to be the strongest line. Instead, we're seeing a lot more of these carbon lines, or calcium lines, sorry, calcium lines. The last classes of stars are K and M stars, and these are the smallest, redder stars. They're cooler and they're fainter than the rest, but because they're small, they're a lot easier to form. You need less stuff to form a K or an M star, and that means there's just a ton of them in the universe. So if we could see every star around us, we would see mostly K and M stars. But they are so faint that we don't see most of them. So there's a ton of them around us, but we don't actually see them because they're much, much fainter than the A stars that we do see. They have weak hydrogen lines because things are just really not hot enough to get the electrons and the hydrogen excited to the levels where we would see the H alpha or H Balmer absorption lines. But what we do see is that there are some neutral metal lines. So kind of a brief note, in astronomy, anything that is not hydrogen or helium is a metal. So anything besides hydrogen or helium is a metal. And in these K stars, we do see these metal lines and these neutral metal lines. So metals that have not been stripped of any electrons, we see their absorption lines for K stars. So that's how we might identify K stars, as well as this kind of low luminosity, low brightness, and red color. So does anyone, before we talk about what makes a star, any questions about the spectral classes? So again, spectral class is based on mostly color, which also tells us the temperature, and then that tells us also a bit about the luminosity of the star. Okay, so I'm not going to put you back in groups because that's too long on Zoom, but I want, if anyone has an idea, what do you think separates a star from a planet? What's the dividing line? So we talked about dwarf planets versus planets. What's the difference between a very big planet like Jupiter and a small star, a K or M star? Anyone has an idea? If you want to shout it out or put it in the chat. So I'm seeing size, potentially size definitely has to do with it. Is there anything else? What makes stars? Yeah, so temperature, composition, but also the really important thing is what Bailey mentioned, is that it's the ability to perform fusion. So if you are a star, you need to be radiating light. To be radiating light, you need to be producing energy somehow, and for stars, that's going to be through fusion. So Jupiter isn't really radiating light. It's not big enough, it's not massive enough to have the conditions necessary to get fusion to happen, but any star will have some amount of fusion going on either in its core or in some of its outer layers. So that's kind of the dividing line, is going to be stars have fusion occurring, planets do not. So, great. Just on that note, though, there are these kind of weird in-between stars. So we had our OBAFGKM. If we want to add on even fainter than M stars, you can add on LTY stars. So with my kind of acronym, that might turn into only brave astronomers fight giant killer monsters like the Yeti, or if you have other Y monsters, you could add in there. But these are stars, we call them brown dwarf stars. They're between about 1/10 of the mass of the sun and 13 times the mass of Jupiter. So 13 times bigger than Jupiter, but only 1/10 of the size of the sun, you're gonna have these brown dwarf stars. They don't have hydrogen fusion happening in the core because they just don't get dense and hot enough to produce hydrogen fusion. But they will have some other types of fusion, some lithium fusion and some helium fusion. So they're still stars, technically, by our definition, but they're just barely stars. There's just a teensy bit of fusion going on. So if you're kind of in this in-between stage, if you're one of these LTY stars, you're not fusing hydrogen like we looked at last week. Instead, you're fusing other materials. But because there is fusion happening, you are still a star. On the other end, so if we jump back really quickly to our main sequence, so we had OBAFGKM, LTY would be kind of over here, faint or even redder, pretty faint way down here. And then there's also these supergiants and giants, as well as white dwarfs that we want to think about. So I'm just gonna back through. So red giants are going to be stars that are much, much larger than the sun, but they are not especially bright or hot. So redder means actually kind of cooler. Red is longer, wavelength lower energy, so it's going to be cooler. They're very, very large. They are stars who are no longer fusing hydrogen, so they've run out of hydrogen to fuse. And because of that, the pressure and gravity balance has kind of been lost within these stars, and they start to expand outwards. And this is part of how stars like the sun die. So if you've ever heard someone say in about 5 billion years, the sun is going to expand and kill us, that is because it is as it goes through its red giant stage. So eventually this will happen to the sun, but we have a lot of time before that happens. So no need to worry about that yet. A fun thing, one star that is pretty easy to find that's a red giant in the sky is Betelgeuse. So that's one of these larger ones here. So the sun, our sun is really small if you compare it to Betelgeuse. Betelgeuse is the head of Orion. So if you go out in the early morning and you see Orion's belt, 3 stars, kind of directly above that, there's going to be a red star, and that's Betelgeuse. Betelgeuse has been undergoing some changes in brightness recently, which make us think that it's potentially kind of close to the end of its life. So it's possible that, you know, in the next 1,000 or so years, Betelgeuse will die, potentially in an explosion. So kind of a fun little fact if you are star watching early in the morning or in spring late at night. So if you wait, Orion will be up. I got a question for Anthony. How common are the brown dwarf stars? So the brown dwarf stars are actually, because they're so low mass, it's going to be pretty easy to find, to form them. You don't need a lot of stuff to make a brown dwarf star. So they're actually very, very common. So there's a ton of brown dwarf stars. I don't know exactly number-wise. It kind of depends on the model you look at. But there's a lot of brown dwarf stars. They're just so faint that we can't see them. You need a telescope to see them, but there are a lot of them. Good question, though. Any other questions or thoughts? On our H diagram, there were red giants, but there were also blue supergiants. So these are going to be extremely massive, very, very hot stars, very, very bright, and they're O and B stars at the end of their life. So the blue stars, when they stop fusing hydrogen, instead of just automatically dying, they start fusing heavier elements. But in this process, again, they kind of lose their nice balance between radiative pressure pushing outwards and gravitational force pushing inwards, and they start changing size. And so we get these supergiants, these blue supergiants. And if you can find blue supergiants, you know they will eventually go supernova, which is cool. And again, we'll talk more about star death next week, right before we finish up this batch. The last type of star on the HR diagram were white dwarf stars. So these were kind of on the opposite side. So jumping back, sorry, we had our supergiants up here in the big stars, bright stars, sometimes blue depending on where you are, sometimes red. White dwarfs are going to be small stars. They're still fairly hot. They're still kind of blue, but they have very, very low luminosities. And that's because these are going to be the remnants of stars like the sun. So once the sun dies, after it blows up into a red giant, it will lose its outer layers, and what will be left is the core of the sun, which will be no longer fusing anything for the most part. So it's whether or not it's a star is a little iffy, but we call them white dwarf stars, or just white dwarfs, so maybe it's not a star. Sorry. But they're very small, they're very dense, and they are still bright because as they collapse, they get really, really hot. So things get dense and hot, and they radiate that thermal energy away slowly over time. So we still see these stars radiating light in the form of this kind of white or blue light coming from these stars. And just to kind of get an idea, so this is the white dwarf stars are very, very dense because you're taking something that's about the mass of the sun and you're shrinking it down to be the size of Earth. So really, really, really high density, which makes them hotter because we're squishing a lot of stuff into a small space. So that turns that gravitational energy of things squishing together into thermal energy that gets radiated away. So before we switch subjects and start talking about the lives of stars, any other questions here? We'll talk more about stellar corpses when we talk about stars dying. Okay, I'm gonna switch. over to now talk just a bit about the lives of stars for the next 25-ish minutes. Sorry, this is a longer lecture today, less material, less activity stuff. When we talk about the stages of a star's life, we're going to kind of split it up into 4 stages. The first stage is stellar birth, so star formation. We can think of this like when the star is a baby. I like to ask when I do outreach, I like ask the little kids, 5th graders, if they have like a baby sibling and how old they think baby stars might be, and they're like maybe 1 or 2 years, and it's like no, baby stars are like million years old. So for stars, for star lives, what is infancy is going to be 0 to about 1 million years old. So that would still be a young star. After that, the stars will start fusing hydrogen, and this is when they are on the main sequence. We can think of this as kind of adolescence or adulthood for a star. So most of a star's life will be on the main sequence. So this is kind of adult life for a star. After it runs out of hydrogen to fuse, it will move off the main sequence and turn into a red giant or a supergiant, depending on its mass. And that's kind of like old age for a star. And then it will die either through a supernova and becoming a black dwarf, a neutron star, or a white dwarf. And that's, stellar deaths, stellar corpses, which we'll talk about in a later lecture. But that's kind of the main idea about a star's life: formation, main sequence, giant phase, death. So the first thing to think about is how we get stars to form. So the birth of a star is when you have a big cloud of gas and dust in a galaxy. So we'll talk about galaxies in our next badge. But when we have a cloud of gas and dust, if things get dense enough that these gas clouds start clumping together, and instead of just being a lot of dispersed gas, you get kind of clumps of gas that can gravitationally pull more and more and more stuff in until you have enough gas clumped together that you form a star. So if things are dense enough in your nebula, in your cloud of gas, you can get that gas to start to condense and form stars. As the clumps get more and more massive, it gets gravitationally easier to pull more gas in until you finally get things that are big enough for it to be a star. So just another note, again, if you're up early in the morning, this is the star forming region in Orion's belt. So if you can find those 3 stars of Orion's belt in the morning, right in the middle, right underneath the belt, there's a stellar nursery where new stars are being formed. It's one of the biggest, brightest ones in our galaxy. Just kind of a cool thing to think about. There's a stellar nursery that I see in the morning, that you can see in the morning too. As this gas starts to clump together, it will also start to rotate. So this will kind of speed up how things are clumping. And you can think of this kind of like when you spin a pizza and the dough starts to flatten out. The same thing happens with the gas cloud. As it starts to rotate, if it starts to spin, it kind of gets flat and denser along a disk with kind of a clump in the middle. So this would be kind of you wouldn't want to eat the center of this pizza because it would be like much more thick, dense dough. But otherwise. So at the center, you have your protostar surrounded by a spinning disk of gas. That gas and dust will collapse to form planets. This is also how planets form. Planets will form at the same time the star forms. So the material that doesn't fall into forming the star will turn into the planets around it. Once you get enough material that things heat up enough, the star gets dense enough for fusion to start, things get dense and hot enough for fusion to start, the stellar winds will start blowing away the rest of the material. So just like we talked about the coronal mass ejections on the sun, as fusion starts, you get these kind of major bursts of energy coming out of the star. You get pressure in the form of radiation that starts to blow away anything that isn't already clumped onto the star or formed into planets. So that makes these really beautiful jets that we see coming off of baby stars. I spelled jets wrong. Sorry, that should say seed jets of gas around new stars, not seed jets of gas. Sorry about that. Yeah, so that is star birth. We have clouds of gas. These clouds of gas get dense enough to start clumping together. The clumps get bigger and bigger as they gravitationally pull more stuff in. They start to rotate, which allows for these kind of pizza disks of gas to form around them, which planets will form out of. Eventually, the star gets enough material, gets dense and hot enough to start fusion, which creates stellar winds and blows away the rest of the material, anything that has not already formed into a planet. Any questions about that star birth, what that looks like? Okay. So once we have finished, that's our stellar infancy, we're now going to move into stellar adolescence / adulthood, and that's going to be the time the star exists on the main sequence. So back in our HR diagram, that kind of chunk, that line going through it where most of the stars are, that's where they're going to spend most of their lives, because when the stars are on the main sequence, that is when they are producing light by fusing hydrogen into helium. So last week when we found out how the sun was creating energy, when we did all those calculations to see how luminous the sun was, we looked at specifically hydrogen fusing to helium. Any star on the main sequence is doing the same thing. It's producing light by fusing hydrogen into helium. Just the rates at which it's doing it might be slightly different. So at this point, the star is also in hydrostatic equilibrium, where the radiation pressure from fusion going out is exactly equal to the gravitational pressure going in. So gravity pushes in, fusion, radiation pushes out, and the star stays the same size while it is on the main sequence. So you're not getting changes with radius. It is in hydrostatic equilibrium, which means it is not changing size. Stars spend about 90% of their lives on the main sequence, so this is most of a star's life is going to be fusing hydrogen into helium with this nice stable state where radiation and gravity are balanced, and it's producing light by fusing hydrogen into helium. We're not going to do this activity. This is the one that I decided to cut. So I do want to really quickly kind of talk through it with you. So we can find the lifetime on the main sequence by comparing the luminosity and mass of other stars to the sun. So when you found the lifetime of the sun, you looked at how bright the sun was and how many fusion reactions it's doing at a time, and then how many fusion reactions it could possibly do to find its lifetime. So we can compare other stars to the sun and sort of write an equation for the lifetime of a star. So if we say the lifetime of the star, I'm going to call that little t. So the lifetime of the star is going to be little t. That should be proportional to, I'm going to regret trying to, I'm not going to try to type this, sorry. We're going to try, I'm going to have to draw this instead, sorry, wasn't thinking. So if I have my lifetime as little t, this is going to be proportional to the amount of stuff the star has to burn. So the amount of fuel, the amount of hydrogen in the star, which is going to be the mass of the star. So it's going to be proportional to the mass of the star, and it's going to be inversely proportional to how fast the star is burning material. So we're going to divide that by the luminosity of the star. So the more stuff the star has to fuse and create energy, the longer it can live, which is why it's proportional to mass. But the brighter the star is, the faster it's using up its fuel. So the higher the luminosity is, the shorter the lifetime will be. The nice thing is, if we always work in solar masses, so if we always take this m to be in m solar, so m with a little o dot, that's going to be a solar mass. If you see that, that means we're working in solar masses. Oh gosh. Sorry for the terrible handwriting. m dot is solar masses, and then if we work in solar luminosities as well, L dot, that's solar. So the luminosity, the sun would have one solar mass. The sun's mass is one solar mass. The sun's luminosity is one solar luminosity. It's just how we define that. If we always work in those units, we can change this from proportionality to an equivalency by saying the lifetime of a star, my little t, is going to be equal to the mass of the star in solar masses divided by the luminosity of the star in solar luminosities multiplied by the lifetime of the sun. So I'm going to call this T solar. So, which is T solar is our lifetime of our sun, which is about 9 billion years. Okay. And we can use that to estimate the lifetimes of other stars. So for example, an O star has a mass of 25 solar masses, so much, much heavier than the sun, 25 times as much mass as the sun. But it has a luminosity, it has a pretty crazy bright luminosity, so a luminosity of 80,000 times that of the sun. So if we plug that into our formula, the lifetime of an O star, T O star, is going to be equal to 25 divided by 80,000 times 9 billion. So I'm just going to call that T solar because that's too hard to write. But plugging in those numbers, we get the lifetime of an O star is about 2.8 million years. So O stars are much, much brighter than the sun. They have a lot more mass, but they live fast and kind of die young. That's how you think of O stars, because they only will be able to fuse hydrogen for about 2.8 million years compared to the sun, which will fuse hydrogen for 9 billion years. So because they are using their fuel so fast, they don't live very long. We can compare that to also K stars. So K stars, I'm going to do this a little faster, I hope, have a mass of about 0.75 solar masses. So these are those small stars, those dwarf stars. And they have a luminosity of only 0.5 that solar, so they're half as bright as the sun. So the lifetime of a K star is going to be 0.75 divided by 0.5 times the lifetime of the sun, which gives us a lifetime of about 13.5 billion years. So what's really cool about that is our universe is also about 13.5 billion years old. So if a K star formed right at the beginning of the universe, it would only be running out of hydrogen now. And because we can't actually form stars in the first few million years of the universe's existence, no K star has died yet. So any K star that has formed in the history of the universe is still alive, which is kind of crazy to think about, just because they live for so long. The main thing, though, I want to highlight is just this equation here, where we can estimate the lifetime of a star by looking at its mass and its luminosity, as long as we work in solar masses and solar luminosities. Any questions there? Cool. I'm going to erase this unless I hear any. Okay. Let's continue moving. So after you've lived on your main sequence life, you have been fusing hydrogen into helium, but eventually you'll run out of hydrogen to fuse into helium, and this is where we start getting into the death of stars, where they start going into old age and turning into giants. But how stars die will depend on their initial mass. So we're going to split this up and look first at how low mass stars die, and then look at how heavier, larger mass stars die. So first kind of F, G, K, M stars, and then we'll look at O, B, and A stars. So once these stars, these low mass stars, have run out of hydrogen in their core, once they've fused all of their hydrogen into helium, fusion will stop because we cannot fuse anything else. They are not hot enough in their core to fuse helium into heavier elements. Because of this, all of a sudden at the core, there is no more radiation pressure balancing gravity. So that hydrostatic equilibrium condition is no longer true in the core of these stars, and the cores will start to collapse. As the core collapses, it will also start to heat up. So as the core collapses, it gets hotter and hotter as it collapses, and eventually it gets hot enough that the layers around the core will start fusing hydrogen into helium. So we'll end up with a small helium core that's collapsing, and the layers around it will start fusing hydrogen into helium and adding to that helium core. So we end up, instead of having a nice stellar envelope with a hydrogen burning core, we end up with a smaller helium core, a hydrogen burning shell, and then the rest of the star that isn't hot enough for fusion to be occurring. So what's kind of confusing about this is that as the core collapses, the layers around the core heat up, and they start producing radiation. So for a brief period of time, there's more radiation coming from those layers around, the hotter layers around the core, which means instead of gravity taking over and the star collapsing, collapsing, and collapsing, radiation pressure actually takes over and the star starts expanding. So radiation pressure and gravity are no longer balanced again, but now radiation pressure is actually higher and the outer layers of the star are expanding. So the core is contracting, but the outer layers are expanding. And this is when we get stars turning into red giant stars. Since the star's surface, so the surface layer of the star is expanding, it's getting further and further away from where the energy is being produced, which means it actually looks cooler. And that's why as the star expands, they become brighter, but they also become redder. So they look lower energy, they look redder and cooler than when they were compact and fusing hydrogen. So after these stars run out of hydrogen to fuse into helium in the core, they start fusing hydrogen into helium in a layer around the core. Their outer layers explode outward. They start to look redder. They turn into red giants. So this is what's eventually going to happen to the sun. It's what's currently happening to Betelgeuse and just any star that will be any F, G, K, or M star will go through this stage once it stops fusing hydrogen into helium. Eventually, in this process, things will get hot enough in that helium core as more and more hydrogen is fused into helium, dumped into the core, which is still collapsing because there's no radiation pressure in that core. So eventually that core will collapse and collapse and collapse and get hot enough that helium will start fusing into carbon. So this begins once that core is about 100 million Kelvin, so very, very, very hot. A neat thing is that happens all at once, all throughout the core in something called the helium flash. And that's because the core, since it is so hot and dense, you can think of this kind of like there's like a traffic jam in the core. So everywhere in the core is the same temperature. There's no temperature gradient. Usually we think closer in it's hotter, further out it's cooler. In these helium cores, everything is the same 100 million Kelvin temperature. And because of that, it all starts fusing helium at the same time. This briefly means that the star will become stable again, as there's a kind of nice source of fusion happening in the core. So the star will stop expanding and it'll just kind of hang out, and it'll start contracting just a little bit, get slightly bluer, and move kind of along in our giant branch. It will start moving back towards the main sequence briefly as it fuses helium to carbon. But this phase will not last long, because the stars will burn through their helium pretty quickly in about 10% of the time they spent on the main sequence. So for the sun, it will fuse hydrogen for about 9 billion years. Then the core will start to collapse, the outer layers will expand, eventually the core will get hot enough to fuse helium, and it will fuse helium for about 1 billion years before it just stops fusing altogether. So once you run out of helium, all that helium has been converted to carbon, so helium gets fused into carbon. We get kind of a layered structure inside of the star where there's a carbon core, where things are really hot and dense and there's no more helium left to fuse. Then there's a layer around that carbon core where helium fusion is occurring. Then there's a layer around that where hydrogen is still fusing to helium. And finally, there's kind of the hydrogen layer around that where no fusion is happening. Eventually, we'll lose this green layer though. We'll just end up with a carbon and oxygen core of this star. There'll be no more helium left to fuse, and the core will start to collapse again. But this time it will never get hot enough to start fusing carbon and oxygen into heavier elements. So that means the core will just keep on contracting, keep on contracting, keep on contracting until it cannot anymore. There will be no radiation pressure to balance out the gravity, so it'll be contracting a lot. And the outer layers of the star will get kind of blown away over time because they won't be close enough to the core to be held on gravitationally. And this produces something called a planetary nebula. So this is the ring nebula, where we'll have a white dwarf star in the center. So this really little dot here, that's the core of the star that's left over. That's almost totally carbon and oxygen. So if you ever hear someone talk about a diamond star, this is kind of that diamond star, because diamonds are carbon. So you have a star totally made out of carbon, which is kind of like a diamond, sort of. Be slightly different structure, but so that's the little white dwarf in the center, surrounded by all the other layers of the star that it is that it is blown away as it collapsed. So you get these very pretty structures we call planetary nebula when that happens. That is where we're going to end for today. Next class, we'll talk about what happens if you are a high mass star, how it's different. And then we'll look at how we can measure the other changes that happen in a star's lifetime. So if anyone has any questions about any of that, I'll answer them now, or you can throw them in the chat. I'm also going to just really quickly ramble a little bit about what else is happening the rest of this week. So tonight I'll be online for labs. All of our labs are now available, but we've kind of covered the stuff in the measuring light, inverse square law, sun lab. We haven't quite gotten to the parallax or the Cepheid or the HR diagram lab, but if you want to take a look at those, you can start looking at them and thinking about them. We've also covered most of the material in the homework. I think only the last couple of questions we have left to get through on the homework. So if you want to start on that, Stellar Science Badge homework assignment, that might be a good thing to think about. The other note I want to point out is that next class, the other astronomy professor, Andrea Dobson, is going to be observing me. So she will be in our Zoom session. She's a wonderful person. If you have a friend who's an astronomy major, they've probably sung her praises. But she will be watching me, not you all. But she will be there, so there will be an extra person in our Zoom meeting. If she asks you a question, please answer. But she's friendly, super nice. So again, observing me, not you, but just a warning that there will be an extra person in our Zoom meeting. And one last thing, I did make a section in our grade book where I'm going to try to keep your points updated for the Stellar Science badge. That is me updating points manually though, so know that it will lag slightly behind where you are, especially with the reading quizzes. So if you're doing reading quizzes, I'll try to keep those updated as often as I can, but know that I will be slightly behind. So if that score looks low, it's possibly because I haven't updated it recently. I will try to do that as frequently as I can, but don't freak out if it looks lower than it should